All right, so continuing here, let's look at this example. So the spatially flat expanding universe here, we have a scale factor which is proportional to time but not space. And so this is a kind of a naive model, like I said, spatially flat expanding universe. So this is just a toy calculation, really, to test our metal with this exterior calculus method. All right, and okay. So first off is to figure out what is to find a frame, right? To find a tetrad. In other words, we need to select not a coordinate, but a frame. I think technically this might actually be a coordinate frame, but that's because it's a pretty simple example as they go. But anyway, here we go. So to find a tetrad, we need to make this equal to that, and so just as Carol mentions, there's many choices, but an easy one is this: just set E0 equal to dt, and E upper I equal to a dxi. All right. So I would point out that means the differential of E0 is just 0. The differential of EI is dA wedge dxi. But because A is only a function of t, that's going to make this dA actually just equal to A dot dt. And then, of course, by the torsion-free condition, we have that this is actually equal to minus the connection, minus this omega wedge, and minus this omega wedge. All right. All right. So let me go on to the next page here. So let's see how that goes. We have obviously you should be watching the last video. This shouldn't make any sense at all unless you've seen the last video, but whatever. So we have, this is our tetrad, all right, dt a dxi, all right. So let's see here, let's run through it. We have the metric compatibility condition is, this, which gives us, of course, that omega 0, 0 is 0, and of course omega 1, 1, omega mu 1, 1, omega mu 2, 2, omega mu 3, 3, all zeros, right? So we only have to worry about distinct indices. Like omega ij is a minus omega ji, and omega 0j is minus omega j0. Now beware that indices up and down do matter here. So like omega ab is a contraction of a to ac with omega cb, like so. So let's see here. Omega 0, upper 0, lower 0 is the contraction of a to 0c with omega c0. Which is just going to give me, so the only time that omega 0c is non-zero is when c equals to 0, in which case it's minus 1. That's why I get minus omega 0, 0 here, right? But we know omega 0, 0 is 0, so that tells us that omega upper 0, lower 0 is 0. All right, great. Now, omega 0j is by definition omega 0c contracted against omega cj. Now, omega 0c, again, is only non-zero when c is equal to 0. And it's minus 1, so that gives us minus omega 0j. So that gives me that. On the other hand, omega j0 is the contraction of omega jc against omega c0. Now this is only 0 if c equals to j, in which case it's 1. Again, I'm always going back to the Minkowski matrix being minus 1, 0, minus 1, 1, 1, 1. And it just so happens that 8 is equal to eta inverse in that context, yeah? So upper, lower 8, I have the same components. That's a very special feature of the Minkowski matrix, but Minkowski metric, but there it is. Okay, so that gives me omega j0. But omega j0 is minus omega 0j, and so we find that omega 0j, omega j0 with the up-down like that, they're both equal. Now, omega ij is related to the contraction of a to ic with omega cj, right? Which, of course, is going to be that. The only way this is non-zero is if c is equal to I, in which case this gives us 1. That's why that's why this simplifies to omega ij. And vice versa, this simplifies to omega ji. Of course, they're equal to minus each other by the metric compatibility condition, which gives us that omega upper I lower j is equal to minus omega upper j lower I. All right, so there it is. You can't just assume antisymmetry, right? I mean, it doesn't make symmetry and antisymmetry is only things you should say if you're talking about sets of indices of the same type, right? So it's I mean, I'm very hesitant to even use that language here, but you know, flipping the j and the 0 gives us a plus, whereas flipping the I and the j gives us a minus, you know. So you gotta work it out. All right, gotta work it out. So all right, so DEA rather equals to minus omega a b wedge omega b. This is the torsion-free condition. Now I'm going to study it. What does it say? So DE0, like I said in the last page, is 0, but that's equal to this. But now we know that this is only non-zero when b is like not equal to 0. So this simplifies to omega 0j ej. It's just sum over j rather than sum over all indices. So yeah, I'm using I and j as if they're going from 1 to 3, whereas a and b range from 0 to 3. Sorry. Physics conventions. I know it'll drive you nuts. And this a is not an index; it's a function of just time. It is what it is. But now, so we have that. So that tells us something, because it tells us like whatever we put for omega 0j, when we wedge it with a dxj, it's got to work out to 0, right? So we got to do that. On the other hand, DEI is this, so we have to have the time derivative of a times dt wedge dxi is equal to this mess. All right, omega I0 wedge dt minus omega ij wedge a dxj. So from 1, if we so this is sometimes productive, like let the connection form be a general form. And a general form in space-time, and the current formalism, it's got a dt part, it's got a spatial part, right? And I'm using a and a sub capital A and capital A sub I as variable placeholders just to keep track of what I'm doing. Now, when I take the wedge product of that and dxj, that gives me this, but of course that has to be equal to 0, and that implies, and the reason that has to be 0 is because this is 0 up here, okay? That implies that we must have that a is 0, because there's no way to cancel this term out except for a to be 0. On the other hand, this has to be 0 for I not equal to j, because there's no way to cancel this out if I is not equal to j. However, if I and j are equal, then this could wedge to 0 and this would still be okay. So this a sub I has to be equal to 0 for I not equal to j. Consequently, only a sub j. Now here j is fixed but arbitrary from that, all right? It could be non-trivial, and that suggests that we should try to make omega 0j equal to a sub j dxj. But then, what is this a sub j? I'm still trying to figure that out, all right? Plug that into 2 up here, and if I do that, that gives me this. And so then I look at it. I want to solve a dot dt wedge dxi equals to a sub I dt wedge dxi minus a times omega ij wedge dxj. So there's probably more than one solution to this, but one solution that pops out at me is just to make this 0, and it's the same one Carol gives, all right? Make this 0. If I make that 0, then I just have to match this, and I can do that by just putting a dot equal to a sub I. And so that's what I do. I put a sub I equal to a dot and omega ij equal to 0. This is a possible solution. And this is the nature of the exterior calculus. It involves these kind of slightly sideways calculations, all right? So, but anyway, so we found that the connection, the spin connection has, for this example, omega 0, 0, 0, omega 0j, a dot dxj, which is equal to omega j0, and omega ij is 0. So that's the spin connection for ds squared. Yeah. Let's see here. So now we can calculate we'd like to calculate the curvature form, all right? So to do that, following the the Cartan structure equations I told you a couple pages ago in the last video, in the last video, right? All right, let me find them just a second here. So going back to page 11, Cartan structure equations. We've got our spin connection, we've got our torsion, we've got our curvature. So we figured out what the omega is. Right now we need to take the exterior derivative of it and then wedge it with itself and add those two things. That should give us the curvature form. So that's what I do. I take the exterior derivative of the spin connection. It's a lot of zeros and then this one non-trivial term, which gives me a double dot dt wedge dxj. I take the wedge product of omega with omega. It's mostly 0 except for this one term with dxi wedge dxj times the derivative of time derivative of a squared. Lo and behold, we have derived that the curvature form has the following components in the tetrad basis. Excuse me, well, yeah, tetrad frame. 0 for 0, 0, 0j is a double dot, I0 is a double dot, and the ij component is just a dot squared. And then, okay, so to be fair, to compare with our earlier approach, we have to use the tetrad. I mean, if you want to, and I do, we have to convert from the Lorentz indices back to the curved indices using the tetrad. Now, what are the tetrad matrices here? Well, the tetrad matrices here, all right. You know, in O'Neill's book, there was a way to calculate this connection just by multiplying basically the analog of the tetrad matrices. There's probably such a thing here as well, and Carol's just not sharing it with us. Maybe it's already been in some of the equations we've looked at. I mean, the thing I just did with sort of ad hoc piecing it together is almost always the fastest way, but there may be a more, I mean, there's certainly going to be a more I don't know what the word is, algorithmically simple formula for it, right? But anyway, simple but tedious formula for it, but that kind of detracts from the beauty. All right, so here's my tetrad matrix, here's my other tetrad matrix, and you can see that from comparing the differential in the coordinate frame versus the tetrad frame and vice versa. So this defines the E mu lower A matrix and the E lower mu upper A matrix. And so like dt has to match dt, right? So that puts a 1 here. dx1 has to match what appears as the coefficient of dx1 here, which is what? Well, it's E1i, which is just equal to A, but that's only if the it has to be that this is if I doesn't not both equal to 1, it has to be 0. So that gives us the 0, 1 over A0, and likewise we get 0, 0, 1 over A0, and this here. And the story is a little bit different over here because we get the A on this side as opposed to that side. So, like for instance, I get A dx1 is equal to this thing times, contracted over dxi, which means that A I1 must be 0 unless I is equal to 1, in which case it has to match the A over here that's implicit within the curses. I haven't written it on this page. Let me go find it again. Back here on page this A, right? Yeah, is by definition A dxi. So anyway, there you go. There's your tetrad matrix here, and then here, um, golly, the whole thing with using different kinds of indices to label different kinds of objects, man, it all breaks down when you get into specific components. And so, because at this point, Carol's like calculating some things. I'm just like, wait, what? What? Oh, okay. So what I found is useful is to just, what I'm doing is I'm putting a couple of underlines under the curved index curvature components, whereas I'll put no underlines under the curvature form components. All right. So you notice that all curved, half curved, half flat. All right, half Lorentz index. And so like, great. Now what I do now is here's what we calculated. Here was our curvature form. If you calculate the mu nu components of these guys, I do that over here. Like the mu nu component of the 0, 0 is, 0. The mu nu component of R0J is, well, it's a little bit complicated, but it looks like this. So it's R0J mu nu. It's going to be non-zero only when we're either looking at 0J or J0, right? Which is reflected in this anti-symmetrized, collection of Kronecker deltas down there. Likewise, for this one and that one, we pick out the a double dot and the a dot squared as appropriate, and like dt wedge dxi gives me the mu nu component being non-zero when either we have mu equals to 0 and nu equals to I, or mu equals to I and nu equal to 0. And similarly down here, we need mu equals to I, nu equals to j, or we need mu equals to I, mu equals to j, nu equals to I. All right, by definition of the wedge product, as it relates to the components of the tensor. So really, I'm just using that like dt wedge dxj is like dt tensor dxj minus dxj tensor dt. That's what's behind this, but anyway. So, all right, then that gives me, for instance, that this R0J0L, which I'm going to get from this one up here, is a double dot Kronecker 0, 0, Kronecker JL, Kronecker 0L, Kronecker J0. Now Kronecker 0L, game over, that's 0 because L is going 1, 2, 3, okay? Whereas this Kronecker delta 0, 0 is 1. Kronecker delta JL will survive, so we got a double dot AJL. Then, to get to the curved Riemann curvature, the curved index component of the Riemann curvature, which I have denoted by our double underline as to help us distinguish, is we have to contract over this pair of tetrads, like so. And if you think about that, the only way for E0A to be non-zero is for A equal to 0. The only way for EJB to be non-zero is for J equals to B, in which case the E0A gives you a what does that give us? Curses. 0A. I think that gives us a 1 in the case A is equal to 0. Right? And this EJB gives us a one of these ups here, A, from the case B is equal to J, which is why I swapped that B out for a J over here. And so then, of course, we already know that that's a double dot Kronecker delta JL, so there you go. That's the Riemann curvature 0J0L component is equal to a double dot times Kronecker delta JL. Continuing in the calculations from page 16, we can show that Ri0K0, so I have to contract over a pair of tetrads And so IA is only non-zero when we have I equals to A, in which case we get a multiplier of 1 over A. This is only non-zero when we have B equal to 0 and the multiplier of 1. And then I multiply by that. Of course, that just sets A equals to I and B equals to 0. So R, I, OK, O, which then, using the formula I had on the previous page, like one of these guys, I get this here, which, let's see here, only this survives because these are automatically 0 because I and K are both ranging from 1 to 3, and of course those are not equal to 0. It just takes one of them to be 0 to make it go away. This one's 1, chronicle like K, so we get that. And then RIJKL, again, pair of tetrads. That forces I equals to A, that forces J equals to B with a multiplier of A with a multiplier of 1 over A. They cancel, and you get this RIJKL, which we saw had components A dot squared, this anti-symmetrized bunch of chronikers. And then you can calculate the, is that my last page? That might be my last page. Might be. All right. And then anyway, so then you can calculate the Ricci tensor by contracting the Riemann. And so if you do that here, you get 3A double dot over A for R00, 0. You get 0 for the other one. And the ijth component of the Ricci, you have the contraction of the 0 and the contraction over the K here. That gives me an A double dot, delta ij, and then this one gives me a 3 delta ij minus delta ij, which gives you, of course, 2 delta ij, and that's the formula that's in Carroll. And I got these just by working through the formulas up here. It's actually, pretty fun to do that. And then, so if we go back to page 333 in Carroll, you can find these formulas, although you might not recognize it at first glance. So here, R00 minus 3A double dot over A. Well, that's exactly what we had, right? Right. Right here, rather. There. This one here is the R11, for example. Like here, 1, 1. So, let's see here, R11. That would give us A double dot, right? And then here you get 3 minus 1. Can you see what I'm... Oh, you can't see what I'm pointing at. Then here you get 3 minus 1, which is 2, A dot squared. And then there's this kappa. And this kappa. But remember, kappa is 0 for us because we're dealing with... So like this is all for the Robertson-Walker metric back over here, right? Which has kappa here. And so essentially what we've been working on is the Robertson-Walker metric with kappa equals to 0. All right, so then you've got dr squared plus r squared d omega squared, which is just simply dx squared plus dy squared plus dz squared. Or if you like, in our current notation, dx1 squared plus dx2 squared plus dz squared. My point is to you is just that we have, in fact, derived these formulas in a way which was, I would argue, it's actually much, much simpler. And I don't know if you can fully appreciate that without doing a lot more calculus in the traditional approach. I can just tell you my own personal experience with this was, when I took general relativity at Stony Brook from Martin Rochek, he used the Cartan approach, and so he showed us these things in that class, and it was, I just thought it was neat. I didn't really appreciate how beautiful it was when I was doing it, but my friend, Tapomoy Guhar Sarkar, had general relativity from one of the elite schools in India, and they had done the other approach, and things that took 3 or 4 pages in the other formalism are like a half page or a page in the current formalism. It is a superior method of calculation, and that's part of the reason that this appendix is in the book. Now, let me just say a few more things. Directions for future study. All right, so one of the things I would mention is this is a wonderful book, Manifolds, Tensors, and Forms by Paul Rentland, an introduction for mathematicians and physicists. I think I've shown you this already, Audric, talking to you. But, in this book, he has a chapter 7 on vector bundles, all right? And here he defines things like, what's a vector bundle, right? It's an assignment of a vector space over each point in the manifold. And you have these things called local trivializations. You basically study how the fibers are attached in a kind of smooth way. You can talk about these transition functions and cocycle conditions, and anyway, all this junk. And then that brings you to, talks about the tangent bundle, and then he brings over here to connections, and he talks about Cartan's moving frames and connections. It's like here, dE is E omega. Anyway, so he's got all these beautiful, somewhat general formulas, the exterior derivative of the section in terms of the product of the connection form, and I've forgotten which is the note. I forgot what the notation means here exactly, but anyway, he has also the curvature forms, the Bianchi identity, and this is all in a slightly more general context, all right? But he also has the general relativity stuff in here as well. So I think this would be a great next thing for you guys to study if you wanted to study something that's still very physicsy, but a little bit deeper with a little bit more details on like some of the things. So there's like a paragraph, roughly a paragraph in Carroll's book or maybe a page where he describes gauge theory. This has more of the mathematics at kind of the same level as Carroll, but a little bit more mathematical sophistication there. All my friends in theoretical physics studied this book, Anomalies in Quantum Field Theory. So this is probably not something you're going to get as a recommendation from a mathematician. But by golly, this book comes out swinging. And in the first 125 pages of this book, you have this beautiful, succinct discussion of differential geometry, topology, and fiber bundles. And of course, and it's got the big picture of modern quantum field theory, which is deeply inculcated with topological constructions and so forth. But skipping ahead to page 112 here, he talks about the connection one form and about the transformation law for the Yang-Mills gauge potential, and it's H inverse AH plus H inverse DH. That's very much akin to the inhomogeneous transformation law we saw for the spin connection, because it was like well, anyway, it's akin to it, and talks about how that in the case of U1 gauge theory, which is electromagnetism, it just becomes the thing you're used to, which is the vector potential. You have a transformation which is just basically adding a total derivative of an arbitrary function. So if you study electromagnetism, you recognize that, but that's just the tip of the iceberg. Okay, so like more generally, it's not like this, it's like that. And this book explains in some detail how that is part and parcel of Cartan's exterior calculus, and let's see here, where was that? Where was that? But anyway, this book also has the exterior calculus as it applies to Yang-Mills theory. All right, and Cartan structure equations again, curvature 2 form for the I think principal bundle here. I could be wrong. Anyway, this is if you want a higher level but still thoroughly physicsy treatment of these things, this is a really nice book to have and look at. It's got, if you want to read about monopoles, instantons, and all kinds of fancier things. Great book. And then this right here is a book which is written by some people who have gone back to the works of Cartan and tried to dig through it and mine it and understand its method more deeply. And so this is an example of a book which will get you into contact with what's called an exterior differential system. So the people who study exterior differential systems, roughly speaking, are really trying to understand differential equations, or perhaps partial differential equations, in a more sophisticated invariant way, which is they're really trying to formalize a lot of the tricks and techniques we use in solving partial differential equations, and trying to understand it as deeply as they can. And so this, I would not say that this is an easy book. It's not one I completely understand yet, but it's deeply fascinating to me, and I recommend it. So anyway, that's it for the moment. I think it would be good. I intend to add that talk on spinners to this playlist, so I'll do that. And anyway, so that's it for now. Thanks, guys.